Hey everybody, so we're back here, and if you saw the previous video of Bennett's Chemistry 12 tutorials, you will know that what we did is we went through, we're in titrations right now, so we went through some of the concepts of why you might need different indicators for different types of titrations, and identifying what those different types of titrations were and why they ended up with pHs at equivalents that weren't always 7. Okay, so we concluded by kind of answering that question right there. Okay, so we answered the question, you've got 3 different categories of titrations. You've got strong, so either strong acid with strong base or vice versa, and they always produced solutions that were neutral at equivalents, and so therefore you anticipated the pH at equivalents to be 7 for a strong titration. The second category was a strong base with a weak acid, and when you did that type of titration, you anticipated the pH at equivalents was going to be greater than 7 because you were making the conjugate base of the weak acid, and so therefore at equivalents you had a solution of a weak base and the pH was above 7. The third category was strong acid with a weak base, and the products of that titration gave you a weak acid. Therefore, you're anticipating the pH at equivalents for that type of titration was going to be below 7, and so therefore all 3 of those different categories required different indicators. So we did that last lecture. Okay, so this one's actually done, and this one is, I decided to do this a lecture on its own simply because it's quite a significant topic as well. Okay, so it was going to be a lot, and we didn't want to take too much time. So the question was, or not the question was, but kind of the concept of this one was that indicators have their own very specific chemistry, and understanding their chemistry and understanding how they work and how you anticipate which one you're going to use and things of that nature, that we want to go through, okay, so that you know when I'm choosing phenolphthalein, why am I choosing phenolphthalein? What is phenolphthalein? How does it change color at a certain pH? All those types of things. Okay, so I'm going to give you quite a bit of detail, and depending on whether or not your teacher goes into full detail or not, you're going to get some detail here. You can always back off, but it's sometimes hard to understand something when you don't quite have enough detail associated with it. So, 2 things you should be able to do. So you should be able to define what transition point means and what it's referring to when we're talking about an indicator. And also the relationship of an indicator's transition point and the value of its Ka, which already should send you some questions should be buzzing around in your brain, simply because what do you mean an indicator has a Ka? Yeah, you'll see in just a minute. The second thing that you should be able to do is you should be able to identify, given a list of indicators and their pH ranges, you should be able to tell me, is this an acid, base, or neutral range indicator? And you should be able to, just looking at that table, you should be able to tell me what color is which indicator at what pH. And also, you should be able to tell me what is its transition point and what is its Ka. You should be able to do that. And then if you're titrating, I mean, from a practical perspective, if you're titrating sodium hydroxide with acetic acid, which of the indicators should you choose? Okay, just keep it that simple. So let's go through a little bit of just generic indicator chemistry at the beginning. So let me erase this, and let me write down a little something here. So indicator molecules, first and foremost, they typically are giant organic compounds. And oftentimes, a lot of the indicators are derivatives of plant molecules. Okay, so you notice out there in the natural world, there's a lot of colorful things that are out there. Well, organic compounds, because of their double bonding structure and ring structure and all these kind of interesting structural components of organic compounds, that they absorb different wavelengths of light. Okay, they're kind of designed out there in nature to do it. Like, this is nature's design. And indicators happen to be able to change color when you change that structure. Okay, so if you alter the organic structure of an indicator, it tends to change its bonding structure and therefore absorbs different wavelengths of color once that structure changes. So I'm not going to draw the organic structure of any of the indicators or anything, but I want you to recognize that indicators have what's known as an acid form and a base form. So the acid form of an indicator is, well, this organic compound obviously has a carboxylic acid group because it has an acid form. So it has a COOH to it. Well, the acid form is the form of that compound where the H is actually stuck on to the carboxylic acid part. And so it would have something like, there'd be some giant R, so some mass of carbons in whatever structure, with a COOH group. So the R standing for the carbons. I'm going to move this over a little bit. When you dissolve it into water, it, like all acids do, will donate some H's over their weak acids. So they donate some H's over to the water molecule, and they make hydronium, and they make the base form. So indicators are really interesting, but they're just acids. They're organic acids. They're large, complex organic acids, and they're not on the Ka table, and you don't talk about them a lot, but they're just acids. That's all they are. So they have an H, they have a carboxylic acid group, they can donate it to water, they can make hydronium, and they have the base form, the COO minus form. So they're not weird from that perspective. They're just these large organic compounds. Now what typically happens is the H, if it's bonded onto this thing, the structure of that compound allows it to absorb certain wavelengths. So it will be one color. So it will be what's known as the acid color. And then you can have the base color. You take the H off of it, and it has the base color. So you might have, for example, an indicator you may have used before in Chemistry 11 or you've seen before is phenolphthalein, that really nice pink one. So phenolphthalein has an acid form where the H is on the compound. It's attached onto it. And so the color of phenolphthalein in its acid form is actually colorless. It doesn't absorb any light. Okay? So it just reflects whatever, and it doesn't look like it's anything. You can't see it. But if it loses its H, okay, and it loses its H and it goes into its base form, well, all of a sudden the base form becomes pink. So it absorbs a whole bunch of wavelengths, but then releases the ones that your eyeball sees, and those wavelengths combined in there make it look pink. And so for phenolphthalein, it has a colorless acid form, and it has a pink base form. Bromethymol blue has a yellow acid form. With the H stuck on, it has a yellow form. You take the H off, give it over to a water molecule, and you form this form of it. It ends up being blue. And so it transitions back and forth depending on how much hydronium is in there. And you can kind of see that any solution of these indicators is, A, it's an equilibrium, and B, would then respond by Le Chatelier shifting depending on how much H plus is in there. If you add H plus, right, so think Le Chatelier, if you add H plus into a solution that has this indicator equilibrium going on back and forth, this goes up, it shifts that way towards the acid form. So lots of hydronium, acidic solution, meaning it goes this way. And you end up with the predominant color being whatever acid form of that indicator you have. When you remove H's, so you're going progressively more and more basic, and by more and more basic, the H3O plus is dropping in concentration. And so if it drops in concentration, you're going to get a shift this way to replace it, because that's what Le Chatelier shifts are all about. You remove something, it shifts to replace it. Well, as you shift this way, you're getting predominantly the base color. You're removing this one and you're getting predominantly the base color. So up in the base range of whatever this thing is, you end up with a predominantly base color. Now, if in the equilibrium you happen to be at a point, now this is, I'm going to plant this seed in your head. If you happen to be at a point where this guy and this guy are approximately equal in concentration, what color are your eyeballs going to pick up? Well, you'll pick up the color. Well, it's the two of them together. It's a mixture. So you got to go back to your grade 1 color wheel, or whenever you learn the color wheel. When you mix two different colors, what's the intermediate color? The transition color between the two of them. So if we're talking bromethymol blue is a perfect example, where the acid form is yellow and the base form is blue. Well, if you have a transition between yellow and blue, like a mixture of yellow and blue paint, what does it look like? It looks green. And so if you have a relatively close balance of acid form and base form of bromethymol blue, you end up with a green-looking solution. Okay? So the transition color depends on the color of a solution depends on the ratio of the acid and base forms at any moment in time. And you can kind of shift from predominantly base acid form over here through a transition where they're kind of close, and so there's that transition color, to a predominantly or primarily base color. And so these indicator molecules will shift from one color to the next with a very distinct transition color when you're on your way back and forth, depending on the pH. Now I'm going to show you a little equation that it's called the Henderson-Hasselbalch Equation. And the Henderson-Hasselbalch Equation allows you to see this concept. Okay, so the Henderson-Hasselbalch Equation comes from the equilibrium constant for an acid. Okay. Now, I'm going to change these things ever so slightly because the equation that's up here is not, it's not wrong. It's just that it's not the typical notation that's going to be used in a chemistry class. So in a chemistry class, what we typically use is, because there's so many indicators that are out there, oftentimes what we do is we use this little notation of IN to indicate indicator. That's like the little symbol for it. So the acid form of an indicator would be HIN. Okay, so the H is stuck onto whatever indicator organic mass of carbons are sitting in there is what the IN is standing for. So that's the acid form of an indicator, which would mean that over here, this is IN minus, is the base form of the indicator. So those two symbols we're going to use all the time. So that's the equilibrium of your typical indicator. Now, if that's the equilibrium of your typical indicator, it's just an acid equilibrium. That's what it looks like, right? It's just these acting as a weak acid, right? HIN, the indicator, is acting as a weak acid. Well, this would have a Ka. And that Ka expression would be hydronium times the IN over the HIN. So there is that mathematical relationship. And so the Ka is just a ratio of all those things, kind of those concentrations all put together in that form. Okay, what if I kind of did a little bit of math here to manipulate this thing, just ever so slightly, to manipulate this guy. So I'm going to manipulate it in kind of an interesting way. I'm going to manipulate it because when you're talking indicators, the ratio of the base to the acid form is kind of critical. So I'm going to kind of chop it right up there on the numerator. And I'm going to rewrite this thing as Ka equals hydronium times, hydronium times the ratio of IN to HIN. Okay, so some of you can see that, okay, so the simple math, that times that would be the top of the fraction, and the HIN is still down there in the bottom. I haven't really done very much, I've just rewritten it in a slightly different form. Now, what if I take a look at this thing and I say, what if the IN minus and the HIN, remember I was talking about that shift from one place to the other, and you go from predominantly the acid form over to predominantly the base form, but somewhere along the line in that shift, the HIN and the IN concentrations in the shift would end up being about equal. Well, what happens if this ratio is actually the IN minus equals the HIN? Well, doesn't that ratio come out to 1? If those two are equal concentration, somewhere during the shift from predominantly acid to predominantly base, somewhere along that shift, this ratio is going to come out to 1. Well, what if that ratio actually was 1? Like at that moment in time during the transition, this ratio equaled 1. Well, then the Ka of the indicator, which is just a weak acid, would equal the hydronium concentration in the water at that moment in time. Because it's times 1. So that's kind of an important thing, because when I was talking about this concentration, the Le Chatelier shifting of an indicator from predominantly acid to predominantly base, had to do with what the concentration of this thing was. So as you manipulate that guy, you make it shift one way or the other. Well, when the hydronium concentration equals the Ka of that indicator, and because it's just a weak acid, it has its own Ka, right? Like all acids have their own Ka. So whenever that hydronium equals the Ka of whatever that indicator acid is, that's when the ratio of HIN to IN minus is exactly 1 to 1. It is the exact transition point. Okay, so when this occurs, you are at the whoa, how do you spell transition? You are at the exact transition point of the indicator. If I negative log both sides, because we know what negative log means, that if I negative log this side, I get something which is the negative log of the Ka, negative log of that is the pH. The pH at the transition point for an indicator. Okay, so that moment when the acid form and the base form are in a perfect 1-to-1 ratio, the pH at which that occurs equals the pKa of the acid. And since acids, these organic acids, are all going to have different strengths, they're going to have different Kas, which means they're going to have different pKas, which means they're going to transition at different pHs. And so, how do I know when these pHs are? Well, we've got a whole new table. So we take a look at our Ka table. Okay, so here's our Ka table. Let's flip the page and let's look at a new table. And this one says acid-base indicators. And the acid-base indicators, and whatever Chemistry 12 course you're in, you're going to have some type of reference that has your indicators in it. And the indicators are always going to have a three columns. One, it's going to have the name of the indicator. Okay, so down this side, I've got the name of the indicator. Some of them you're familiar with, you've heard of them before. Some of them are totally foreign and you've never heard of it before. Fair enough, there's lots of indicators that are out there. Then you're going to get a pH range. And the pH range is telling you, okay, so I'm going to put this pretty close there. Hopefully you can see it. And if you can't see it, hopefully you've got your own table to be referring to. So the range that's given to you, the lower number, means that below this value, you are predominantly in acid form, and therefore you have the acid form color of that indicator. The higher number of the range means that if you are above this number, you have predominantly base form of this indicator, and you therefore have the base form color above this number. So I'll give you an example, and I'll point to it, and maybe you can see it, maybe you can't see it. Okay, so I'm going to go to bromethymol blue. Okay, so bromethymol blue, which is right there, it's almost the middle one in this list. And bromethymol blue has a range, according to this, of 6.0 to 7.6. So the low number is 6.0, the high number is 7.6. That means below 6.0. So if you take bromethymol blue and you put it into a solution that has a pH lower than 6, it doesn't even matter what the pH. If it was 5 or 1, it doesn't matter. It's going to be the same color. So anything below 6 is going to be, according to over here, okay, so you come to the other side and it says yellow. So anything below 6.0 will make bromethymol blue be predominantly its acid form, and that will be predominantly yellow. So you're going to see yellow. That's what you see. Because the upper range says 7.6, that above 7.6, you are going to see primarily the base form. And the base form, according to this, says blue. And so above 7.6, bromethymol blue will be predominantly blue, and it will look blue. You'll see blue. Well, what is it in between? Well, anywhere in between, you are going to get varying shades of a mixture of yellow to blue, anywhere in that range. So if you were at 6.1, you're going to start seeing a mixture of yellow and blue. Granted, it will be probably mostly yellow, so it's going to be kind of a slightly greenish yellow. If you were at 7.5, well, it's almost blue, so it will be kind of aqua, kind of blue or greeny blue kind of thing. Well, where is it going to look perfectly green? Where's the perfect green? Well, the perfect green, I guess logically, would be halfway across that range, right? Doesn't that make sense? That, okay, so if it's mostly yellow kind of down in the 6.1 range, and it's mostly blue at like the 7.5 range, right in the middle, you would have that perfect transition color between yellow and blue, which would be green. And you'd be right, because halfway through that range is exactly where you have equal amounts of the acid and base range of that indicator, where you have the 1-to-1 ratio of those two things, and therefore you have this, and therefore you have that. So these are pH ranges. The exact midpoint of that range is the pH known as the transition point. Okay, so for bromethymol blue, where the low end of the range is 6.0 and the upper range is 7.6, halfway through that would be, well, okay, so subtract them, 1.6, divide by 2, so that's 0.8. So 6.8, yeah, you can also just add the two together, divide by 2, take the average. You get 6.8. So at a pH of 6.8 for bromethymol blue, that is the perfect transition point. And so at that perfect transition point, you're going to see the perfect green at 6.8. Okay, now how does all of this apply to anything? Okay, well, let's just take a quick look at another one. Okay, so let's use a different indicator. So keep in mind that the bromethymol blue had the perfect transition point at 6.8. I'm choosing that one for a very specific reason. 6.8 is really close to 7. So then let's look at phenolphthalein, which is another common one that you use down here. So phenolphthalein, right there. So phenolphthalein has a range of 8.2 to 10. Okay, so it's down there. It says 8. If you can't see it, trust me, it says 8.2 to 10. And it goes from colorless to pink, according to this. So its acid form is colorless, and its base form is pink. Now, what's the transition color between colorless and pink? Well, I don't know, light pink. So it's like just a hint of pink. And if you've ever seen phenolphthalein in a truly basic solution, it is like that hot pink color. Like there's no mistaking that you've got pink. When you've got phenolphthalein actually in that transition range, it's a very faint pink, and you can tell that it's just a very faint pink. So the range is from 8.2 to 10. So using the same concept of halfway across that range is the perfect transition for phenolphthalein. 8.2 plus 10 is 18.2. Halfway is 9.1. So the transition point of phenolphthalein occurs at a pH of 9.1. Okay, so bromethymol blue, perfect transition where it hits that green, was exactly at 6.8. Phenolphthalein, being a different organic acid, has a perfect transition of 9.1. Well, you wouldn't want to use those two indicators for the same transition, right? Because one's changing at around 7 and one's changing at around 9, two different things. So now let's put that into our understanding of titrations. Titrations, where up here you're anticipating, you're predicting, I'm doing this titration, I predict at equivalence it's going to have this pH. Well, I don't want an indicator that's changing at a pH of 7 when I'm anticipating the equivalence pH is going to be 9. Why would I do that? I'm going to stop I'm going to see a color change too early. Like, I'm not there yet. I'm not even at the equivalence yet, and yet I would have stopped because I saw the color change, right? That's called the end point. You would have ended your titration. Well, you'd be wrong. You're not even at equivalence yet. Same thing the other way around. Why would you use phenolphthalein when you're anticipating the titration is going to have a pH of 7 at equivalence? Once you see the transition color of phenolphthalein, you actually start to see some pink forming. Well, you're already up to pH of 9. Well, you've passed your anticipated pH of 7. You've gone too far. Your endpoint is too late. You missed it. So choosing an indicator for the proper range is critical, right? You want to use the right one so that you're in the neighborhood. Now, nothing's going to be perfect. Bromethymol blue does not give you the perfect transition point at 7. It's 6.8. It's pretty darn close. It's the closest one you can get on this table. So it is a neutral range indicator because it has a range that covers 7. Trust me, you will not be able to see the color difference between 6.8 and 7.0 for bromethymol blue. And nor do any of us have the skill with our titration and using the burette to be able to make that slight difference. The change is happening so rapidly at that point, you couldn't change it from 6.8 to 7 if you even tried. You couldn't make a drop small enough. So we're using something like bromethymol blue for a neutral range pH change. So for strong titrations, where we're anticipating a pH of 7, we would use bromethymol blue as our indicator because it has a range that contains the 7 that we want. When we're talking about a strong base with a weak acid, and we're anticipating an equivalence pH above 7, and if you recall what I said in a previous lecture, was most of them are between 8.5 and 10.5. Well, phenolphthalein is perfect for that. Like, it covers 90% of titrations of weak acids. Why? Just because it has that proper range. Somewhere around 9 is where you're going to start seeing that color change, which is an indication that you've hit equivalence for that type of titration. The one that we typically use, and there's different ones that are in the lab, but if you've got a strong acid with a weak base, you're anticipating an equivalence pH below 7. And the one that tends to work the best for that is brome cressyl green. And brome cressyl green happens to have a range. So brome cressyl green, where's brome cressyl green? Is right here. 3.8 to 5.4. So it has a pH at transition of 3.8 plus 5.4 is 9.2, divided by 2 is 4.6. So it has a pH of about 4.6 at its transition point, which covers the majority of what you're going to have. Sometimes you might go down to a methyl orange, which is a little bit lower. So it has one at 3.8. It's a little bit on the lower side, so you'd be, if you were anticipating you were going to get a slightly lower pH at equivalence because of the products of your titration, you might go with that. That one's kind of hard to see because it goes from red to yellow and yellow to red. So seeing orange is a challenge in there. And that's kind of the concept of it. And it has to do with the fact that these indicators change color depending on whatever that concentration is in the water. Okay, and that's kind of that transition point is kind of a critical thing why indicators actually work and why we're choosing different ones for different types of titrations. Okay, now you could go even deeper into this stuff because knowing this concept, that you can actually determine the Ka of an indicator, and you can actually, indicators are weak acids, so you could calculate the pH of a 1 molar solution of phenolphthalein at 25 degrees with an IRE table and everything else, because you can calculate what its Ka is supposed to be. It's just the connection is here. So given your table, if you were to take halfway across the transition range for any one of these indicators, that's the pH at its transition. That is its pKa. If you go 10 to the negative pKa, you get the Ka value of the acid. And you can go from there. Once you know the Ka of an acid, you should be able to do the calculation of its pH. Okay, so those are the indicators, and that's kind of the concept of why we're choosing certain ones for different ranges. And you combine that with the previous lecture, you get the idea of why you're going to get different pHs at equivalence and why you need these different indicators for different types of titrations. So hopefully that really helped out. That's a lot beyond what you knew from titration in Chemistry 11. And yes, there's a lot more subtlety. So when your teacher says we're using phenolphthalein as the indicator for this titration, it's because we're anticipating a pH at equivalence above 7, right? So now it's not just, oh, well, he grabbed that one off of or she grabbed that one off of the shelf, and that's the one that we're using today for no apparent reason. There are a lot of reasons behind it. So hopefully you got that. We'll come back next class, and what we're doing next class is we're actually going to start getting into the titration. So, okay, you've got all the kind of the subtleties of these titrations and the pHs at equivalence and indicator choice and all that kind of stuff. So now let's get into the what do we do when we actually do a titration. We get some values from it. What types of calculations are we doing? So we'll start that next class. Okay? Good luck with your chemistry, and we will see you soon.